Well, good morning, y'all. And I apologize for not being in class today, but that doesn't mean you can't learn, right? So here we go. Let's continue with our considers. We're in our discussion of thermochem, and we come up with this question here. I have 311 grams of water at 22 degrees Celsius. How much heat is needed to raise its temperature? So we want to talk a little bit more about heat, and specifically, we need to get into this idea of specific heat. So let's talk for a second, right? Oops, need to, there we go. Let's change the color. Yoink, yoink. Okay, I think we're good. So we want to talk about heat. And I guess what I'd like to talk a little bit about here is heat transfer, right? Heat transfer. And I think we're all familiar with the most important term in heat transfer, right? The equation that we use for heat transfer, and that is Q equals mc sub P delta T, right? And this means what? Heat is equal to the mass, the heat transfer is equal to the mass of the body times this thing C sub P times delta T, where delta T is equal to my T final minus my T initial. And it's important to understand here that delta T in degrees Celsius is exactly the same thing as delta T in Kelvin, that I don't have to do any converting as long as they are both in the same degree. So if they're both in Celsius, I can leave them both in Celsius. If they're both in Kelvin, I can leave them both in Kelvin, because 1 degree of Celsius, 1 unit of Celsius is exactly the same as 1 unit in Kelvin. Good. I want to focus a little bit of our time here on this concept of specific heat. So let's come down here and let's write some notes on things related to specific heat. First, I want you to understand the concept of heat capacity. Heat capacity, good. So what is heat capacity? And it's C. It is the amount of heat required to raise the temp of a sample, any sample, a sample of a substance 1 degree Celsius. Good. Now, these units are usually joules per degree Celsius or joules per degree Kelvin. And, excuse me, not that degree of Kelvin. Now, heat capacity is not that common for us. We don't run into it that often. There's another related concept, which is molar heat capacity. And that's usually connoted by a C with a molar. And that is the amount of heat required to do what? To raise temp of what? Well, if it's molar, that would mean of 1 mole of substance, 1 degree Celsius. And so my units here are joules per mole degree Celsius or joules per mole Kelvin. All right, good. And the one that we are somewhat familiar with from last year, in case you recall, and that is what we call the specific heat. Specific heat, usually C sub P, in some, sometimes it's connoted as an S. You'll see in some of my considers I have it as an S, but C sub P, I think, is the more common designation. It's the amount of heat required to raise temp of how much? 1 gram of substance, 1 degree Celsius. So the units here are joules per gram Celsius or joules per gram Kelvin. All right, so now we know something about C sub P, and I think then we can go to our questions and answer it. Are you ready? Here we go. So I want to know how much heat, so that means Q equals MC sub P delta T. What's my substance? Water. Aha, water. The C sub P of water, of liquid water, is 4.184 joules per gram Kelvin. Got it? And you don't need to memorize that, but it comes up quite common. It is quite common. What's my mass? 311. What's my, it starts at 22 degrees. That means it's my T initial. It is raised to T final. So I have Q equals 311 grams times 4.184 joules per gram Kelvin times my delta T, 98.0 minus 22.0 degrees Celsius. And so what do I get out of that? First, though, I want to look at this, right? We want to look right here. That's the first thing I kind of want to look at. 22 minus 98 looks to me like that's 76.0. How many sig figs do I get out of that? I get 3 out of that. Okay, so we'll take 76.0, 76 times 4.184 times 311. And that gives me 98893. How many sig figs? Looks like I can get 3. So that's going to be 98900 joules. Good. Let's kill that. It's bothering me. There we go. All right. So you guys try the next one. Right here. Bring me back when you have an answer. All right. I have 25 grams of aluminum. It starts at 325, so that looks like this is mass. This will be my TI. How much heat is released? I want to know Q. When the aluminum is cooled to TF. The S, also known as C sub P, is 0.90 for aluminum. Here we go. Q equals M, 25.0 grams. C sub P, 0.90 joules per gram Kelvin. And delta T, what's my TF? 298K minus, what's my TI? 325K. And let's run the numbers. I'm going to start over here with my temps. 298 minus 325, and out of that I get a negative 27. Notice what's happened to my sigs. I've gone from 3 sig figs to 2 sig figs. So now let's put this into my equation and multiply it by these two things. Times 0.9 times 25, and it looks to me like I get a negative 607.5. How many sig figs? 2. So that would be a negative 610 joules. And now notice I have a negative value here. What does that imply? It means that heat is released. When I have a negative value, heat is released. Good. Moving on. Let's get a little more complicated here. Now, in this case, I have 25 grams of aluminum. I know what the C sub P is for aluminum. It's dropped in 311 grams of water. I know that. What is the final temp of the mixture? Okay, here's what we have to know, and maybe we should go back to our notes here. Let's move this down. Oops, I need to start over here. So let's go this way. Extend page. Good. So let's talk about heat exchange, or heat transfer. I really like the word transfer, right? Heat transfer between two bodies. Ooh, two bodies. Good. And in this case, one of those bodies, in this case, we're looking at one of the bodies being water. So here's what we have to understand. Our basic assumption is what? What's the basic assumption here? The basic assumption. All heat lost by body one is gained by body number two. So that would mean Q, body one, is equal to the negative of Q, body two, right? They both have the same magnitude. The only thing that's different is the sign. One indicates that it's losing, and the positive indicates that it is gaining heat. The negative indicates it's losing heat. Good. So that's the key concept here in these kinds of questions where I have two bodies and heat is being transferred between them. So let's go back to our question. I have two bodies, right? I have aluminum and I have water. I always like drawing a picture here to help me better understand things. So here we go. I've got some water in here, right? How much water do I have? It says I have 311 grams of water. So this is my mass of W, we'll call it. Good. It says that it is dropped into water at 22 degrees Celsius. Okay, so that means my T initial for water is equal to 22.0 degrees Celsius. We don't know the final T water. T final water, unknown. Good. I do know the C sub P of water, right? C sub P water, 4.184 joules per gram Kelvin. And what do I know? I'm dropping a chunk of aluminum in here. Here's my aluminum. It says that aluminum has a mass of, so my mass of aluminum is equal to 25.0 grams. What else do we know? It has at. So what is that? Is that an initial temperature or a final temperature? Well, that is a initial temperature of my aluminum. So that's 325 Kelvin. And I do know that the C sub P for aluminum is equal to, what did we say from that last question? 0. Let's check it out, make sure we're right. I think it's 0.90, right? So here we go. Aluminum, 0.90. Okay, good. So we know that this is equal to 0.90 joules per gram Kelvin. Got it. Now, we have to find the final temp for both of these. And what do you know about the final temp? T final aluminum. What do you know about the final temp of both of those? Well, here's the issue. We know that, what is heat? Heat is the transfer of energy from bodies at two different temperatures. When will my heat stop transferring from the aluminum to the water? Well, what do we say? Heat just is the transfer of energy between bodies of different temps. So my question is, when will the heat stop? Well, it'll stop when what? When the bodies both have the same temp. So at the same temp, heat stops. And we call the things coming to at we say when things are at the same temp that they reach thermal equilibrium. So things at the same temp, we say that is a thermal equilibrium. Equilibrium. Good. Thermal equilibrium. So what's going to happen here is that the aluminum and the water are going to reach thermal equilibrium, meaning that TF aluminum will equal TF water. They will both come to the same temperature eventually. Got it? Okay, so if we know these things, we can work this problem. Here we go. We need to do one other thing. My temperature for aluminum is in Kelvin. My temperature for water is Celsius. We should convert both of these to the same. So let's take our Celsius 22.0 plus 273.15, and I'll get 295.15. But remember that 5 is not significant here, right? Kelvin. All right, now we can do our job. First, let's write the equation for Q aluminum. Q aluminum is equal to M aluminum, C sub P aluminum, delta T aluminum. Good. We also know something about water. Q water is equal to M water, C sub P water, delta T water. Got it? Cool. What else do we know? Well, what do we know about the heat transfer? We know that all the heat lost by the aluminum has to end up going into the water. So that means Q aluminum is equal to negative Q water. Okay, so it looks to me like we have another equation. Here we go. Let's work it. So let's set these equal to each other. That means M aluminum, C sub P aluminum, delta T aluminum equals negative, yoink, parenthesis, mass water, C sub P water, delta T water. Good. Let's start substituting. What was my mass aluminum? 25. So I have 25.0 grams. The C sub P is 9.0 joules per gram Kelvin. My delta T, what's my final TF? We don't know. What's my initial? I think it's 325, right? 325K. 325K. Let's do the same thing then. On the other side, I have a negative. What was my initial mass? 311. 311 grams. Let's put a bracket here. Times, what's my C sub P? 4.184 joules per gram Kelvin. Times my T final minus 295.15 Kelvin. Got it? All right. We just have to solve this now. Here we go. I'm going to take 25 times 0.9 equals, so I have 22.5 times TF minus 325K, and that's equal to a negative 311 times 4.184, which looks to me to be 1,301 times TF minus 295.15K, right? Okay, so now let's continue doing our algebra. So we're going to take our 22.5, so I have 22.5 TF minus, okay, so now let's take our 22.5 times 325, and I get what? 7,312.5, and that's equal to, now let's distribute this, a negative 1,301 TF. A negative times a negative is a positive, plus, recall 2 times 295.15, and I get, how about something along the lines of 384056. Good. Let's collect terms. This is going to come over here, yoink, and this is going to come over here, yoink. Good. So let's take my 22.5 plus 1301, and I get a 1323.5 TF is equal to plus 7312.5. I get some wacky number that looks like 391,368. Good. Divide by both sides by 1323.5, and I get a 295.7 as my answer. Does that make some sense? I guess it does. It means that my temperature of my water was only slightly affected, right, by that aluminum because I had so much water. However, the temperature of my aluminum was very effective. Okay, you guys try the next one. Bring me back when you are ready. Here it is. All right, same kind of thing. Let's draw a picture. So first thing I do, draw the picture. Right, I have water in here, and my water is, what did it say? My T initial water is equal to 20.0 degrees Celsius. Says the final temp, oh, okay, so I have a TF water. This is going to be a little easier to do. 35.5 degrees Celsius. What is the mass of the water? So we need to find mass of the water. Good. And we do know the C sub P of my liquid water, and that is 4.184 joules per gram Kelvin. What do we know about the iron? So we drop a chunk of iron in here, and we know that this is 18.8 grams. So that's my mass of iron. We know the C sub P of iron is equal to 0.45 joules per gram Kelvin. And what do I know about it? 18 at, I know my initial temp of iron is equal to 20.0 degrees Celsius. Good. Do I know anything else? The final temp of the water is 35. Okay, if the final temp of my water is 35.5, we can assume what? Thermal equilibrium. So we know that the TF of my iron is the same as the TF of my water, which is going to be 35.5 degrees Celsius. Got it? All right. So we have everything we need to know for our irons. Let's calculate Q iron. Q iron is equal to M, 18.8 grams. C sub P, 0.45 joules per gram Kelvin. Delta T, what's my T final? 35.5 minus 20.0 degrees Celsius. What's my calculation here? 35.5 minus 20, and out of that I'm going to get a 15.5, so that means I still have 3 sig figs, times my 0.4 times 18.8, and my answer is 116.56. I only have, what, oops, I hope I did that right. Let's check it. I maybe made a mistake. Okay, 15.5 times 0.45, I couldn't read my own writing, times 18.8, how about 131.13? I missed that 5 there. It looked like a joule to me. I have 2 sig figs here. That means I can only have 2 sig figs here. Now that's my QF, so what's my Q water? Q water is going to be negative Q iron, so that's going to be a negative 131.13 joules, and then we know Q water also equals what? M water, we're trying to find that. C sub P water, 4.184 joules per gram Kelvin, and delta T water. Delta T water is 35.5 minus 20.0. I made a mistake here somewhere, didn't I? Ay, caramba! We made a big mistake. Yoink, what was my mistake? Right there. Sorry, folks. Yoink. Here we go. My TF my T initial, excuse me, for iron was not 20 degrees. It was 229 degrees. Ach du Lieber. 229 degrees Celsius. 229 degrees Celsius? Yes, 229 degrees Celsius. So that means my TF is 35.5 degrees Celsius minus 229 degrees Celsius. There we go. Sorry, folks, you guys probably all caught that. 35.5 minus 229, and I get a negative 193.5, but it's only significant to the 193 times 0.45 times 18.8, and I get, here we go, I get a negative 1637 joules. Good. And so that's my QFE. So my Q water is the same magnitude, different sign. There we go. 1637. How many sig figs can I get out of this? I can only get 3 out of this. There we go. That's going to be equal to my mass water, which we need to find, times my C sub P, 4.184 joules per gram Kelvin, times my delta T, 35.5 minus 20.0 degrees Celsius. Got it? Okay, let's solve for MW, which is going to be equal, divide by 4.184, divide by quantity 35.5 minus 20, and I get an answer of 25.2 grams. Let's make sure. I'll try that again. 1637 divided by 4.184 divided by the quantity 35.5 minus 20, and I get 25.4 at 25.24. There you go. I hope this helped you. When you're done with this, watch the next lecture on coffee cup calorimetry. All right. I will see you when I come back from the break. Bye.